Good morning, students. In the last class, we discussed JK flip-flop, right? And in today's class, we will see uh, what is the disadvantage of JK flip-flop and how to overcome that with the help of JK MasterSlave, right? So in the last class, we have seen the disadvantage of SR flip-flop, which is set reset flip-flop. When S is equal to 1, R is equal to 1, we will get a forbidden state in which outputs are not complement to each other, right? So to avoid that, we use JK flip-flop, right? So, and what is the advantage of JK flip-flop? It has removed the forbidden state of a SR flip-flop, and the outputs will be complement to each other when J is equal to and K is equal to 1. J is equal to K is equal to 1, and this has formed one more problem of toggling, right? So the last state of a JK flip-flop is called a toggling, right? So what do we mean by toggling? See, now let us say if this is a clock which has a very low frequency, let us say which has very low frequency. So what I am explaining you the disadvantage of what? JK flip-flop. Disadvantage of JK flip-flop, right? So let us assume this is a clock which has very less frequency, and if I keep J is equal to K is equal to 1, let us say J is 1 throughout the clock frequency, and K is also equal to 1 throughout the clock, right? So now what happens? Let us say I am talking about this level, or I am talking about this edge, right? So we have two types of flip-flops. One is called the level triggered flip-flop, and one is called the edge triggered flip-flop. Actually, you don't have any in detail discussion on these two types of flip-flops, right? So let us understand in short what is the level triggered flip-flop and edge triggered flip-flop. So in case of level triggered, right, so the flip-flop is going to work as a flip-flop or a memory device only when this particular level is detected by the flip-flop. Let us say again, level triggered has of two types. One is low level triggered and high level triggered, right? So when level is high, let us say this is high level and this is called a low level, right? So let me change the ink of the pen. See, this is a low level, this is high level, and this is low level, right? So if flip-flop is responding for these levels, then they are called as level triggered flip-flops, right? And if they are responding for these edges, right? So similarly, similar to these levels, we have two edges in a clock, right? So one is called a positive edge, second one is a negative edge. What do you mean by positive edge? Whenever the value of a clock changes from 0 to 1, right? So we get a positive edge and or a rising edge, you can say, and a negative edge means whenever the clock value changes from 1 to 0, then we will get a negative edge, or you can say the falling edge, right? So you can see the two markings, two arrow marks here. So this here the value of clock is changing from low is also denoted as 0, high is also denoted as 1, right? So here the clock value is changing from 0 to 1, and here it is changing from 1 to 0, right? So here we will get two types of flip-flops, two types of edge triggered flip-flops, right? So in which the flip-flop is going to respond only for this rising edge, or it is going to respond only for this falling edge, okay? So when it responds for these edges, then they are called as edge triggered flip-flops, right? So now let us assume we are talking about edge triggered flip-flop, right? So you have multiple edges here, multiple positive edge as well as negative edge. Let me precise, we are talking about a positive edge triggered flip-flop, right? So that means whenever the clock changes from 0 to 1, whenever the clock changes from 0 to 1, during that edge the flip-flop is going to change its output or its state, right? So now we will see how this what happens. So what is the disadvantage of JK flip flop with this, right? So what happens here, see J and K both are high. What happens to the value of Q? I'll take only the value of Q. The later value you can identify, that is Q bar. You can say if Q is equal to 0, Q bar equal to 1. If Q is 1, then Q bar is equal to 0. If this is 0 to 1, here also this is the first positive edge. 0 to 1 it is changing, right? So since Q, let us say the previous state is Q is equal to 0 and Q bar is equal to 1, right? This was the previous state. So what happens when we make J is equal to K is equal to 1 and it has detected a positive edge, then Q will become 1. Q will become 1. Initially it was 0, Q will become 1 and Q bar will become 0, right? So Q bar will become 0. Initially it was 1 and here initially it was 0. So now it will change to 1 and 0, right? So this state, it will not remain in its this state, right? So again when it detects the second rising edge, this is the second rising edge, again J and K are kept high, right? So here again the value of Q and Q bar will change, right? The same thing repeats whenever that particular flip flop detects a rising edge. So at a given certain amount of time, we do not get a stable state of Q and Q bar, right? So as soon as we make J is equal to K equal to 1 and we keep it high for a longer time, and if the clock frequency is more, it doesn't happen in case of clock frequency which has very less, right? So if it has less clock frequency, then we don't have a problem of JK, we don't have a problem of toggling, right? It arises only when the clock frequency is very less, and in such case we do not find a stable state of that particular JK flip flop, right? So continuously Q and Q bar is going to vary like this, right? So we do not find any stable state, right? So this is the problem with this is the disadvantage of JK flip flop, right? I think you understood. When the control input has a very high frequency, then we cannot say in which state the a JK flip flop is, right? So it is going to continuously change its state, right? So this particular changing of the state with respect to the control input is called toggling. So this toggling itself is a disadvantage of JK flip flop, right? So to avoid this toggling, we will go with a JK master slave, right? So you can, with the help with the name itself, you can identify there are two JKs in this master slave. One acts as a master, one acts as a slave, right? So whatever master tells, the slave just follows, right? So and how it avoids this toggling state, that we will see in next slide. Okay, so now I'll explain how the JK master slave works and how it can be seen. What is the circuit diagram of JK master slave? Okay, so this is JK master slave, right? So as the name itself tells, it has two JKs. One acts as a master, one acts as a slave. So let me draw the circuit diagram of this. Okay, it's again very simple. Same two JK flip flops you draw, but there is a slight modification in the first JK flip flop, right? So here I will be taking only this feedback. I am not giving see, in the previous diagram of JK I had given this Q bar. I will denote this as QM and QM bar. What M stands for? M stands for master, right? So here this is the control input, which we call it as clock. Then this is J and this is K. Okay, you can call it as JM, inputs for master, right? And this is KM, right? So but here if you see the diagram of JK flip flop, I have one more feedback path from QM bar, which is connected to the first NAND gate, right? Let me number this NAND gates. QM bar is connected to one of the input of first NAND gate, and QM is also connected to one input of second NAND gate, right? So this is the little modification. So that path we are not showing here, we are shifting those paths to the output of slave, right? So what I'll do here, see, again the same 4 NAND gates I am taking. I am drawing again one more JK flip-flop, right? So here these are the outputs of slaves. So what I'll do now, I'll connect this QS to one of the input and QS bar. Let me number these 5, 6, 7 and 8. There are total 8 NAND gates, and this acts as a control, and this QM bar is connected to. So what are these inputs now? I'll denote this as JS and these as KS, right? So this is one more JK flip-flop, and this is first JK flip-flop, and this is, I'll denote it as clock S, clock control input for a slave, and this is control input for master, right? So what is the modification here? I have to negate or I have to complement these control inputs, and I have to connect them, right? So between two control inputs I need to connect one inverter, right? So this is the setup, right? One more modification, this QS is connected to second NAND gate, and this QS bar needs to be connected to the first NAND gate, right? Let me correct it. So I'll connect this QS to second NAND gate, and the QS bar is connected to the third input of first NAND gate, right? So this is the circuit diagram of JK MasterSlave, right? So now let me explain this circuit diagram, right? So now what happens, I'll write 2 JKs and complete all clock M. This is the input for control input for master. Next, control input for slave. Inputs of slave, that is JS and KS. These are the inputs of master. These are the inputs of slave. Then I'll write the outputs of masters and outputs of slave. Alright. Now, clock M, let us assume the first input which we are going to apply for clock M, that is control input, is 1, right? So if I make control input is equal to 0, that particular NAND gate will not, that particular flip-flop will not be enabled, and it will not work as a JK flip-flop, right? So to work as a JK flip-flop, I need to keep that control input is equal to 1, right? So everything will remain same for 0, 0, 0, 1 and 1, 0. The states are going to remain same, right? So only two states I will explain, that is 0, 1 and 1, 1. How to avoid that toggling state, that is important. Okay, so I will explain it for 0, 1. Let us say 0 and KM is 1, and let us assume the previous state is 1, 0, slave state is 1, 0. Here we are going to see the output of slave, because these two are my final outputs. So these are the intermediate outputs, QM and QM bar, regarding which we are not talking about. Okay, so we are talking about only the QS and QS bar, which will become my final outputs. Okay, so now when JM is equal to 0, KM is equal to 0, what you are expecting at the slave end? At the slave end, you are expecting, because KM is high, you are expecting QS is equal to 0 and QS bar is equal to 1, right? So let us take this as the control input, right? So clock M, clock S we are not providing externally, because only clock M we are providing externally, and the complemented output of clock M is connected to clock S, right? So if this is clock M, and if this is 1, or when it changes from 0 to 1, this edge you take, either you take that edge or level, that doesn't matter, clock M will become 1. So when let us say Q1, what is the state of QM? You can assume anything, you can assume either 0 1 or 1 0, it's left to you, but I want the final state needs to be changed according to the inputs, right? So now when clock M is equal to 1 0, clock S will be equal to 0, right? So when clock M is equal to 1, clock S is equal to 0. That means slave, this is slave, this part is slave, which is disabled because clock S is 0. Clock S is 0, slave is disabled, and only master is enabled, right? So at a time only one flip flop is enabled depending on the control input. If clock M is 1, this is 1, JM is 0, the output of first NAND gate is equal to 1, and this is 1, this is 1, and this output, previous state of the slave is 1. So this 1, this is 1, this is 1, all three are high, output of second NAND gate is 0, right? Since one of the output of one of the input of fourth NAND gate is 0, output will become 1, that is QM bar will become 1, and this QM bar is connected to second input of third NAND gate, so 1 NAND 1 is equal to 0, right? So this is the state of the flip flop, right? So because see, KM is 1, KM is 1, right? So QM you got equal to 0 and QM bar is equal to 1 as per the truth table of JK flip flop. Now, so when it changes its state from 1 to 0, this during this rising edge, falling edge, what happens? Even though the input changes here, clock M will be equal to 0, right? The main control signal, control input, which is clock M, is becoming 0, right? So once it becomes 0, even though JM and KM changes, the output of output of master will not change, right? So only the output of slave will change, because when clock M becomes 0, clock S will become high, right? So when clock S will become high, and only slave will be enabled and master is disabled. Even though you change JM and KM, the output of slave will not be output of master will not be affected, only the output of slave will be affected, because only slave is enabled, right? So when clock M becomes 0 during this falling edge, clock S will become 1, that means slave is enabled. Since this is 1, QM is 0, since one of the input of fifth NAND gate is 0, output is 1, and this is 1, KS is also 1, because QM bar is directly connected to KS. Since KS is 1, clock S is 1, 1 NAND 1 is equal to 0. Since one of the input of 8th NAND gate is 0, output of 8th NAND gate will be equal to 1. Did I get QS bar is equal to 1? Yes, that means QS I need to get as 0. Just check. QS bar is 1, 1 NAND 1 is equal to 0, right? So when JM is 0, KM is 1, QS is equal to 0 and QS bar is equal to 1. So these are my final output, right? So this is not a change. Even this is same as the JK flip flop output, right? So when it changes, when JM and KM both are high, right? So let us take again clock M is equal to 1. We will take 1 and 1 now. 1 and 1, right? So during the positive edge of the clock, then what happens here? Let me clear. So now you can see when JM is equal to KM is equal to 1, and KM is equal to 1, when I make both JM KM high and clock 1 is applied, 1 NAND 1 output is, it also depends on the third input. QS bar is, this will act as a previous state, QS bar is also 1, so these three will be equal to 1, 1 1 1, output is 0, and here one of the input is 0, because QS is 0, output of second NAND gate will be equal to 1, right? Since this input is 0, output of third NAND gate will be equal to 1, right? Is it toggled? Yes, 0 1 was the previous state of master. Now when I make JM equal to KM is equal to 1, it has toggled, right? So 1 NAND 1, QM bar will become 0, right? So when we get the falling edge, clock S will become 1, right? Since this is 1, QM is 1, QM bar is 0, output of NAND gate will become 1, right? And output of fifth NAND gate will become 0, right? Since output of fifth NAND gate is 0 and one of the input of 7 NAND gate is 0, so output of 7 NAND gate will become 1. So this 1 NAND 1, QS bar is equal to 1. Is it toggled? QS bar is equal to 0. Is it toggled? Yes, right? So even if I keep Jm is equal to Km is equal to high, we do not get any change in the master slave